choice. So this rectangle, the area of the rectangle changes as the point swings around on this function, which is what? If we describe the function that the y-coordinate is coming from.
Square root.
It looks like a circle, doesn't it? Well, a semicircle, a hemicircle. Anyway, so we're told a lot of information in this little paragraph. Lots of words. These are the kind of problems on multiple choice, no calculator, that are stressful, I think, because it's not actually too bad, but there's a lot of reading and it's technical and it's sometimes hard to sift through. Anyway, we have the derivative given of our function and we have critical points given. This one, for some reason, this 2 didn't highlight, kind of like the others, so there's also a 2 there. And then we're told that a prime changes from positive to negative at x equals root 2. Positive to negative means what? Yeah, so it's a max. Okay. So what do you think? The inscribed rectangle with maximum area. First of all, we know since we're told that it changes from positive to negative that we're going to be talking about a max. So right away we can kick out B and D. So now it's just kind of algebra, right? Like plug in root 2 into the y-coordinate. Well, x and y coordinate. Only thing is make sure that you don't miss that the area is actually 2x, right? So maybe plug it in here as well. So you should end up picking C. How'd you do?
Good.
Raise your hand if you got it.
C? It's always
C
C.
seems to be a safe bet. All right, squeeze theorem. Raise your hand on that one. Yeah.
Okay, it's like a limit must exist when the values from the left and right are the same at a certain point. Like at the same point. This is squeeze theorem, right?
I don't think, I wouldn't use the words left and right.
Negative and positive.
Because that was like the 1 and 2-sided limits idea, right? The squeeze theorem is more this way. It's weird because it formats, when we write it out, it formats like a left and right thing. Maybe that's what you're saying. But it's really a top and bottom thing, writer.
If you have two functions that intersect at the same point and a third function that goes between them, the third function will hit that point.
Good. Okay. So I think I know probably what you're thinking, but keep in mind, this was kind of the classic example picture. If we know that if those two parabolas have a limit of 0, and then we had like this crazy function that skinnied down through there, and then it came on the other side looking wild again. Well, we could say that the limit as x approaches 0 is the same as those two parabolas' limit, as long as, let's call this f, g, and h, as long as we knew that this was true. G, I'm doing it very kind of quick notation. Okay, so the limit had to be squeezed in between the limits of the other two. So as long as that was true, then we could say that the limit of h was the same as those two. What were the restrictions or the failure points of this? Like when we said, no, we can't use it. Yeah, so if g and f had different values, then we couldn't say it got squeezed in between because there was room for it to wiggle through there, so to speak, without it hitting a single value. Okay, what else? Yeah. Okay, yeah, if we weren't told that the inequality was true, if that was not told to be holding true. And then the other one was if the limits as g and f went to whatever value, if those didn't exist, then the limit wasn't going to exist either. Okay, does that ring a bell? We haven't said squeeze theorem in probably a couple months now.
Many years.
Do you feel like you remembered it okay? Okay. Remember, we're coming up on your final in, what, like 9 days, I think? 8 or 9 days? Yeah. The final is going to be 11 questions on Unit 5, so kind of a Unit 5 final test, and then 14 questions on the whole semester. Okay? Huh? Nah, you don't need it.
What do you have you seen our test scores lately? Yeah.
Lately? We're going to review. So today's stuff is the last new stuff. We're going to use optimization on Thursday in class just to give it a shot. We'll talk, hopefully, we'll talk about your progress checks tomorrow. So if you have any questions on those. And then just kind of in there, we'll review too. So, do you need a paper review or can you just review FRQs and in class?
Yeah.
Oh my
I think you
goodness.
should just make the test for review.
That doesn't sound like an AP class. All right, give this one a shot. I realize now that it is really small. You don't need the picture totally, so we'll do the best we can with that. This one, you do need to write some stuff down on, so
Okay, thank you. Here, can I draw it?
I don't know, can you? Guys, this is a good one. This is an AP style question. It's more involved than you think for being a multiple choice. Okay, here's the idea of this one. We always have to connect back to the origin. So we're saying, of all these lines, which one has the smallest slope? Okay? So we're always connecting a point on the function back to the origin. Okay? So you can kind of see, like, right, if the point was there, it's pretty steep. It's steeper than the one they showed. If the point is here, it's less steep than the one they showed. But then eventually, as this parabola comes up further, it will get more steep again, right? So there's some point in there where, I don't know, maybe in here where it's the least steep. Now, this has nothing to do with the tangent line. Did everybody read that? Okay, so we need an expression for the slope. So recall, this is our general, like, Algebra 1 version, is that. So let's go fill it in now and do some calculus on it. So for this problem specifically, what do we plug in? What's y2? What's y2? We don't know, right? But it's this. Did everybody see what I'm saying by that? Okay, what is y1? It's always connecting to the origin. So what is y1? 0. Okay. What is x2? It's just x, because that's what we're solving for. And then minus 0. Okay? All right, so our slope function, whoops. Our slope function, just simplified out a little bit. Looks like that. Okay, what do we do with that? That's our slope function. And so thinking of optimizing, what is our next step? We're already in one variable. So what's our next step to optimize that slope? take the derivative, right? So in order to know where this has a minimum, we need to take its derivative. Please do that. Everybody in the room, take the derivative of that. Let's call it m prime. Okay, so here's it's quotient rule in this case. I haven't simplified yet, but just so it's low d high minus high, and then d low is just 1, so I didn't write that. Okay, low d high minus high d low over low squared. Okay, now we can simplify that because there's a lot going on. So we get 2x squared minus x. Oh, and on this, make sure you write that whole thing in parentheses so you don't miss the sign. Minus x squared plus x minus 16. Okay, if you notice, the two, I wrote that wrong. That is not. Hold on, I lost a term. Let me rewrite it. Sorry about that. 2x squared minus x squared plus x minus 16. There we go. Those two x's cancel, and then 2x squared minus x squared is just x squared. So we get x squared minus 16 over x squared. Everybody good on that? Okay. Now what? We have our derivative. It's simplified. What do we do with it? We want to minimize the slope. So what's next?
Take the square root.
Critical points, right? The only places we know there are minimums are either endpoints and critical points. Well, we don't have to check endpoints. Well, we can, but let's do this. So actually, we do have to check that. Let me say that the right way. But m prime equals 0 when what? That's our critical point. Yeah, so when x squared minus 16 equals 0. Okay, so that happens at x equals positive and negative 4. But look at our interval. Do we need to worry about negative? Nope. Okay, so just worry about the positive 4. Okay, are we done? Can we just say it's at 4 since that's an option? No. We really should check the slope value at 1, 4, and at 8. But we can kick out C now, because that's not a critical point or an end point. Okay, and then we just plug this in. So 1 squared minus 1 is 1, is 0, and then 16 plus 16 is just 16. Okay, 4 squared is 16 minus 4 is 12, plus 16 is 28. And then 8 squared is 64 minus 8 is 56, plus 16, whatever. It's definitely not the smallest, right? Right? I'm just going to say not the smallest. All right, anyway. What do you know at this point? Hmm? Say what you're going to say. Okay. Okay, so we are on the right track, but I wrote something wrong, and we did it wrong, which is what? This is just m. Just the function's value. So it's not the slope. Do you see what I'm saying? I think that's what you're saying. So m should be divided by x. So let me write that. I just found the numerator, not the denominator, if that makes sense. Are we clear now? Okay. So m of 1 was 16. But divided by 1 is still 16. M of 4 was 28, but divided by 4 is 7. Okay, and then M of 8, I didn't actually finish that one. 8 squared minus 8 was 56, plus 16 was 72, over 8, so that's 9. Okay. So we should have chosen B. That's a lot of work for a multiple choice question, right? And a multiple choice with no calculator. So that's a 2-minute problem if you were just breaking it down on average time. That's tough, right? This is why on the ones that are shorter, you want to bank time as much as you can, is bank time. Any questions on it? All good? Okay. Any questions before we do this? Any questions on the test prep problems? Okay. All right, last section. Exploring behaviors of implicit. You guys remember implicit differentiation? Well, this is our last specific focus on derivative stuff. Next semester, we shift over to integrals or antiderivatives. We'll still be taking derivatives, but not like what we've done. I think you're going to like that stuff. It's cool. So I'm excited to start that semester. Implicit relationships still follow the same rules. So if dy dx equals 0 or does not exist, there's a critical point. Highlight that. It's kind of buried in here. But it makes sense. Dy dx we know is a slope. Of an implicitly defined function. So if it equals 0 there, then it's probably a minimum or maximum. Okay, and then similarly, if the second derivative is greater than 0, it's concave up, etc. Okay, and if it's less than 0, it's concave down. All right, well, we know we're going to start by finding dy dx. So go ahead and do that just as a quick review of the function there. While you're finding that, what are we going to look for to know if the function is increasing or decreasing there? Yeah, so just the sign of the first derivative will tell us. So dy dx. Okay, well, this one is going to be with respect to x, like we wrote, so it's going to be 9x squared. And we don't need to do any d after that, right? It would, I mean, if we did, it would be dx dx, which is just 1. What's the derivative of 3? 0. What's the derivative of natural log? 1 over, in this case, 1 over u, so 1 over 4y squared. What's the derivative of 4y squared? 8y dy dx. Good. And it's times, not plus or anything like that. Okay, so dy dx is not alone, but it's showing at least. We can see it. All right, so we really just want to know if dy dx is positive or negative. That's really the question. So is dy dx positive or negative? Do we need to isolate dy dx before we can answer that question? No. So we can plug in now, or we can isolate and plug in a little while later. One thing we could do, though, is simplify this on the right side. 8 divided by 4 is 2. Y divided by y squared is y in the denominator, like so. Okay? So again, you could just you could multiply by y over 2 and then get dy dx by itself if you want. You don't have to, though. So dy dx is 9x squared y over 2, if you want. Again, you can do either version for answering this problem. Okay, and then we plug in. So I'm going to move over here. And we're going to say dy dx evaluated at x equals -1, y equals 1/2. Okay, well, since we only care about the sign, this is positive. It is 9/4, but we only care if it's positive, right? So is this increasing or decreasing? Okay, this is kind of interesting. We can't say like f is increasing because we don't have a name. It's just the curve. So the curve is increasing because dy dx is greater than 0. Actually, we do need to state the point. Let's do that. At x equals -1, y equals 1/2 is greater than 0. Okay, so it's very similar to what we've done. Actually, we've done implicit differentiation. We've also found whether something is increasing or decreasing. Now we're just combining those two. Any questions on that one? Seem okay? Okay, how about concavity? True. So he said f double prime. But what has to be true first?
F prime has to be 0.
Okay. So f prime, we don't have an f, but let's just keep using that language, has to be 0 first. Then we can do that. So go ahead and I'm going to give you 2 minutes to take both derivatives. So first and second derivative of this curve. Okay, just giving you some feedback. First derivative should be 2x over e to the y. Okay, that's now, we take the derivative of that, which is now quotient rule. So we have low d high minus high d low, including the dy dx, over low squared. Okay, and then remember, this is where we plug in dy dx that we had the first time back in to get the actual derivative. And you can see some stuff will, well, one thing will cancel there. If you want to, the e to the y will simplify out. Or you can plug in. You know, if you don't want to get too deep into the algebra, you can start plugging in at that point. All right. I'm going to just plug in. So do you guys remember the notation? Actually, it was at the top of the page, so never mind. d2y over dx squared equals, or evaluated at, at x equals negative 2, y equals 0. All right, all this plugging in. Okay, 2e to the 0 is what? 2. And then minus, or negative 2 times negative 2 is plus 4. E to the 0 again is 1, so I'm not going to write, I'll write it. 2, I'm here now. 2 times negative 2 is negative 4 over 1. And then this is just 1 squared. Okay. So we get the denominator is just 1. So we get 2 minus 16 is negative 14. Not that we care about the actual value, but the sign in this case. Okay, the curve is concave down because why? We gotta say d, yeah, good, is what? Yep, good. Now, we said at the beginning of this that the first derivative had to be 0, but for concavity it doesn't have to. That's for combining concavity with the max or min, right? So just determining concavity, we can only look at the second derivative. But if you look down here at the bottom, the last question, now it's saying, is it a max, min, or neither? Now we've got to combine the first derivative being 0 and the second derivative's concavity. So second derivative test would be my suggestion. Could you do it with just the first derivative? Can you determine if a point is a max, min, or neither using only the first derivative?
Yes.
Yeah. You just have to make the little table, right? Like find the critical points and then decide where it goes negative to positive, positive to negative. You can do that. It might be more work in this case, but you can. Okay, so first, and since we're talking this way, let's do it as f prime equals 0 and then the sign of f double prime. But f prime has to be 0. If it's not, then we can't use this test. So let's check it first. Now, again, we have to not use f prime when we do the problem. So we're evaluating at the point x equals 0, y equals 1. So that is 2 times 0 over 3 times 1 squared minus 1. So is 0, 1 a critical point? Yeah, this equals 0. So 0, 1 is a critical point. And we can continue. What if it had been any other number? Or DNE? what would we pick then? We would say it's neither, right? Like if this had equaled anything else but 0, we would say neither. Because there isn't a critical point there, that's what we would say. All right, now we've got to go check the sign of the second derivative. So same point, we're still evaluating at x equals 0, y equals 1. Now it's just a lot of being careful with signs and stuff. Okay. Well, what happens to that whole second part of our second derivative when we plug in x equals 0? That whole thing is just 0, right? So this is going to be 2 over 3 minus 1, which is 2 over 2, which is 1. And then the big deal there is that it's positive. Everybody following, or are we going too fast? Good? Okay. So what do we have at this point? We have a critical point with a concave which way? Yep, this is concave up. So we have a relative minimum. All right. Do the odd ones and the test prep tonight. If you need an extension on the multiple choice, let me know because I want to check that tomorrow.
I did it. I got all the way through.
So just writer. I already did yours. Okay, you guys have a good day.
Hey,
Hey,
you too, man.
me too. What?
Have a good night.
Oh,
So Thursday we're just kind of doing a review.
no, we're going to do a optimization little exercise.
Okay, I'm not gonna be here Thursday, so what can I do to make that up?
You can just do it on your own.
Okay,
Yeah.
all right.
There's nothing special required.
All right. Can I get this stuff from you tomorrow
Yep.
for Thursday?
Yep.
Okay, awesome. Thank you.
Yeah, no problem.
You would never. You would never. No, you would never. You legally could, but like you wouldn't. Because it would only take like 2 shots to kill me. So like, you agree with me?